Hey guys, welcome to today's lecture. So a brief anecdote. I'm not going to name this person, but this person was a student, as a PhD student with Professor Tarbell, who, if you know, was not in this space at all. And this person graduated with a PhD in BME, in a cardiovascular lab, and is now director of data science at Johnson & Johnson. And so I think that's very, obviously this person has probably had to work very hard to get to that position, but I think it kind of illustrates the flexibility. I mean, first of all, the flexibility of BME, but also just that you don't necessarily, to work in this space, you don't necessarily have to even come out of a lab that does research in this space. It's very much the skill set, I think, is quite accessible to you, as long as you have the mathematical framework, which you all do because you're all engineers. And so I think that's and this kind of, and the reason I bring it up now is because my motivation for trying to get to the deep learning section earlier than usual is that I think that those are the types of things where if you've just been exposed to it and you know how to put together a basic script in Jupyter, to train, test, tune a model, I think it could go a long way. Before we get there, kernels were pretty much the, kind of the go-to. And so what I'd like to do here is just with a kind of a toy example, demonstrate the radial basis function support vector machine. So to do this, we will create data that is where one class is distributed, has examples in, I'll just draw it. Actually, you know what? Let me just execute the code. So the code this is on the Blackboard. It's called demo kernel SVM2. And so I'll just kind of point you to some of the kind of key lines of code. So the function rand is outputting uniform random numbers between 0 and 1. So rand n is normally distributed numbers. Rand is just uniform. So if I type in rand, you'll see it will always be a number between 0 and 1. Rand n, first of all, can be positive, can also be negative, and it's unbounded. So it's not necessarily between 0 and 1. Rand is a uniform distribution. And so here we are generating 100 points. We're generating 100 radiuses, essentially. And in the line below, we're generating 100 polar angles. So 2 pi of a uniform random number. And then we're just using we're transforming the randomly generated numbers from polar coordinates to Cartesian here. The RNG1, by the way, this random number generation with the one is called a seed. And so if this is important if you're working like in a team and you are comparing different models of different algorithms. Anytime there's randomness, you have to make sure that the seed is the same. So random number generators, they're not actually random. That's number one. It's actually the way that computers generate random numbers is with a sequence, it's like a recursion equation. And so where that sequence starts is called the seed. And that determines all future outcomes. And so there was that guy, I don't know, it was like 30 years ago now, that figured out, he like tracked, if you've ever, you're too young and too cool to ever play Keno at a casino, but if you've ever played Keno, it's just like a bunch of numbers coming up, and if you get a certain number of numbers on your card, you win. And so there was a guy that basically went in every day, I think all day, for like a couple of years and tracked the numbers and was able to figure out the parameters of the random number generator. And he won the jackpot 2 times in a row, and I think was sued, and then I went to court. But anyhow, I say good for him for figuring out their process for generating random numbers. And definitely they've had to, I'm sure they've had to add more complexity to the way they generate those numbers now. So we're gonna generate, oh yeah, what I want to say around number generation. If I type a random, if I initialize our random number generation with a seed of 1, and then I type in, and then let's say I ask it for 5 Gaussians, I'll see this. So let me actually clear all. Let me see. I'll say range 1 and then random 5 1. So I get that. And then I'll clear all again. So you should, this really should be tested again from another machine. But if I go range 2 and I get different numbers. And the idea is that as long as, even if you're on a different machine, as long as you initialize this seed, this parameter, to the same value as somebody else, you should always get the same results, no matter how complicated your code is, no matter how much randomness is involved. You should always get the same outcomes. So that's important on like team projects, is everyone has to agree on the seed. So that's what we're doing here with the RNG1. So we're gonna generate 2 clouds of data. Cloud 1 has a radius of 1, and cloud 2 has a radius of so let me actually ask you a question. Let's say that U is, I call it X actually, is distributed with a uniform distribution between 0 and 1. If now Y I define as 3 times X plus 1, what is the distribution of Y? So X is uniformly distributed between 0 and 1, and Y is specified as 3X times 1. What is going to be the distribution of Y?
1 to 4.
Yeah, that's right. It's going to be 1 to 4, exactly. So this is how when they actually, I took a stats class in my second year where, and I don't think they normally teach this, but he's the one that taught me all about this random number generation, all these like numerical recipes for how to generate different distributions. And so that's exactly right. So so the way you generate, if you need your range to be different, you can add an offset to every number, and you can multiply every number. So this controls the range, and this controls the offset. And so what's happening here is that the radius. So actually, this is going to be a radius of 1, and this is going to be a radius of 2, because we're taking a square root. So square root of 1 is 1, square root of 4 is 2. So this is going to be a radius. The radius of R2 is going to be between 1 and 2. And the radius of this, the first guy, is going to be between 0 and 1. And then the angles are just random. So let's go ahead and execute this. So we're going to use this Matlab function, easy polar, which is exactly what it says. It's a easy polar graph. It's just a way of graphing graphing stuff in polar coordinates. So I'll show you, first of all, the clouds of data. All right, so the red points are class number 1, and the blue points are class number 2. And then I can also just draw on top of that the corresponding radiuses. And so what you see here is,
Professor, the blue one's a ring. It's not a circle, right?
that's right, it's a ring, yeah.
Because it's starting at 1, right?
That's right, exactly. Exactly. The blue one is like a ring. So yeah, so the red one, so the radius of these of the data in polar coordinates is uniformly distributed. For the red class, it's between 0 and 1, and for the blue class, it's between 1 and 2, right? So we have perfect separability here. I don't think it's possible for this data to not be separable. However, it's only separable with with a circular classifier. Like this is not linearly separable. Or with a polynomial, actually. I don't think a polynomial kernel could separate this either. Like I don't think a hyperbola, I may be wrong on this. Maybe a super high degree polynomial could do this, but I'm not sure. So this data really needs our radial basis function kernel, as you can see. And so what we're gonna do now is we're just gonna assign fake labels to this. So we're gonna say that the first 100, the red points, there's 100 of them, belong to the negative class. So the class is just the label, right? So, the class of 1 points 1 to 100 is -1, and then the label of the remaining points is going to be +1, right? So we just have, so the red points are one class, the negative class, and the blue points are the positive class. And now what we're going to do, and this is the key line of code here. We are going to fit a radial basis function support vector machine model to this data. And so data 3s are X. So we could have called this X. So for example, size of data 3 is 200 by 2. So 200 examples, 2 dimensions, 2 features, and size of the class is 200 by 1. And then we tell the program that we want to use the radial basis function kernel. The box constraint is something that I'm going to skip over the regularization in support vector machines because it's very mathematical and it's not difficult to implement and it's not difficult to understand really. It's just a bunch of equations, but essentially box constraint is just a way of telling the support vector machine how much error you're willing to tolerate. So 1 means you're not willing to tolerate any error. 0 would mean you're willing to tolerate a lot of error. So this is just a way of telling the support vector machine that we believe that this data is quite separable, and so don't regularize it. And then this is just the class names. We're just calling the first class -1 and the second class +1. We could give them, we don't have to use -1 and +1. We could use whatever, we can put whatever labels we want in here. And so now, this is the first really important line of code. So we can evaluate this, and I will, oh, I guess it didn't run. Let's see. Excuse me. So we're going to look at the output of CL. So what we see is that CL is an object. It's an SVM classification object that has 200 that has 200 examples in it. And we see that if I look at the sum of cl.is support vector, should be 47. And that means that 47 of the data points here, 47 of the markers here have been designated as support vectors. So can anyone guess where the support vectors are going to be in this example?
At the radius of 1 or the boundary between the two regions.
Exactly. It's going to be near the boundary of the two. And we're actually going to plot the support vectors in this demo. So that's right. It's probably going to be the ones that are near a radius of 1. And so let's actually, just to give you a little bit more programming insight or whatever, let's actually try to see index support vector. I'm going to say is find cl.is. So now I'm going to have the indices into these are going to be my 47 indices that correspond, right? So these are the support vectors. And what I'm interested in and now I want to create another variable called radius support vector is equal to, so I'm going to say data 3. Excuse me. And so I'm going to say, so this is in Cartesian. And so what I have to do to get the radius of each row of each example is I'm going to square it. And then I'm going to sum it. And then I'm going to square root it. I haven't practiced this before class, so if this doesn't fit, if this fails, I apologize, but I'm going to try it. I'm going to try to prove my point here. So radius support vector. So let's see what so these are the radiuses of the ones that were chosen to be support vectors. And you see that they're all pretty close to 1. And so if I look at mean radius support vector, it should be 1. And if I look at the mean of, let's make radius all. I can select all. Oh, actually, this is, yeah, I'm not sure this is going to work. The radius all, the mean of radius all can still be, that's still, but if you see, you'll see when we actually,
it's a normal distribution, right?
Yeah, exactly. But the point is that there's going to be numbers here that are far away from, there's ones here that are 0 radius, and there's ones here that are close to 2. And so those will not be the support vectors, right? And so the point is that the ones that it chooses as the support vectors are the ones that have a radius close to 1. And you're going to see that here. So now comes the other important line of code. So it's pretty standard to, you're going to have your API, which is like just the term that is used for when somebody writes some software and they want to be other people to be able to use it, they create an API, which is like, here are all the functions and here are their specifications. So your machine learning API will always have a fit function, which is here where you give it X and Y and you fit a model, you figure out the model parameters. And then you will also need a function that makes predictions. So this is given model CL, predict the label. So my question to you is why, this may be, so this code here, this block of code from line 35 to 39. So if you remember, mesh grid literally just creates the X and Y coordinates across some regular grid. And so these 4 lines basically create, you know, if I, let's see, how do I plot it? So for example, X1 grid, how big is this? Let's see. So maybe I'll image it. So X1 grid, I think I've shown you this before. Right, so X1 is just the X, you know, as you go from left to right, the values get larger, and then X2 is the Y-axis. So the numbers get larger as you go from top to bottom, because the Y-axis is increasing as you go down. And so, so that's X1 grid and X2 grid. And then this line here basically reshapes. So the size of X1 grid is, you know, it's basically a regular grid. And what I'm doing in this line of code is I'm flattening this matrix. So 198 times 197 will be 39,006. So what I'm taking all the X coordinates and I'm flattening them. And I'm taking all the Y coordinates and I'm flattening them. And I'm putting them into a single, an array that has the 39,006 rows and 2 columns. So now this array, X grid, is still holding the grid. It's not holding it. It's not holding it in a square. It's holding it into this, you know, very tall rectangle. And the reason for that is I want to evaluate the classifier that was just learned up above. So classifier CL, I want to make a prediction for every point on the grid. And so, if I'm actually going to go to the help for this, because there's something else that we are using. So the predict, let's see. The predict function generally will, hold on. I want to see the, this is one of these, this is one of these examples, one of these functions where the function predict is called, it's called overloaded. It's an overloaded function, which means that the same function name is used for multiple in multiple libraries. So you got to find a help file for the library that you're going to use. So this is the help I was looking for. So the predict function takes 2 arguments. The first argument is your model, which we just fit. That's our argument CL. And the second parameter is our data, our feature vector X. But what I want to draw your attention to is that there's actually 2 outputs. There's a label and there's a score. So the label is actually, you know, which class does X belong to? But the score is like it's your soft prediction. So remember in logistic regression, we had, and this is true for any kind of really any learning algorithm, we had something like we had sine, or maybe a step function, but I'll just leave it a sine, W transpose times X plus B. And that becomes our Y hat. And so, you know, Y hat is either going to be -1 or +1. And so that's just the predicted label, because it's you're projecting the data point onto your model, and then you're comparing it to 0. So another way to think about this is you apply your model to X, and then you threshold it against 0. But sometimes you're interested in not just which class each example belongs to. You're actually interested in the how close were you to being designated to the other class. So, if you have your number line, and let's say that this, let's say that this is let's say you're thresholding to 0. Your data, will generally look like, generally have some distribution. And so everything to the left here is going to get assigned to the negative class. And everything to the right of 0 is going to get assigned to the positive class. However, an example out here has a different interpretation than an example out here. So the scores are the values, are the continuous predictions before thresholding. And we're not actually, these will be the labels here. These will be the labels here. The one that the argument, that little tilde here, the little tilde here means that I don't care about that argument, that output. So I'm ignoring labels and I'm just keeping scores. And so what I'm going after here are these continuous predictions before the thresholding against 0. And the reason for that is I want to actually plot the prediction across the entire grid as a contour plot. And so what I'm going to do here, I'm going to plot the data again, and I'm going to indicate which are the support vectors by basically putting a black circle around each marker that was a support vector. And in addition to that, I'm going to plot these scores as a contour plot. What that's going to do is going to show me where in the space, where in the two-dimensional space the classifier is going to predict a positive class, and where in the space the classifier is going to predict a negative class. And so let's go ahead and evaluate this. What? Are you kidding me? Oh. So here's what it looks like. And so there are, first of all, let's look at the support vectors. Those are the ones that have the black circle around it. So indeed, you see that the points that are close to the boundary are designated as the support vectors. And so everything that's far away, like this example, is not informative to the classifier. Why? Because it is not a good example to use as a template for deciding between red and blue, right? The template between red and blue is really critical to sample the points that are near the unit circle, basically. So unit circle is this inner circle, and this of kind of circular looking thing, but not quite a circular, is the contour. It's the contour of it's basically the decision boundary. And so if I go back to the picture, what we've basically asked the function contour is to tell me the contour that corresponds to a prediction of 0. So in that Gaussian distribution, I'm looking for where is the boundary between positive and negative class, essentially. And what's interesting is that it hasn't quite learned, it's come close to learning the unit circle, but it hasn't. I think if we gave it more data, and actually maybe I'll do that in a second, if I give it more data, maybe it will do a better job of learning the unit circle. Because we actually see that there would be mistakes here made, right? I believe if I compute the, let me see, where's the data? Actually, I don't even need this. I need to call the predict function. This is just the training data, but I will evaluate it because it looks like it looks like it would actually make mistakes, even though the data. Okay, so. It's called the predicted labels. Let's actually call this predicted scores. And so now let's look at the accuracy. So the mean of pred labels is equal to, it's called the class, 98%. So it's pretty good, but there are actually mistakes made, right? And you can see this blue one here is on the wrong side of the decision boundary. It's actually doing perfectly on the red class, but it's making mistakes in the blue class. Some of the blue examples have appeared on the wrong side of the boundary. And so one way, if I, let's say that I increase the number of data points. So I have to go through, let's say I go up to 500. And now let's run this. Huh. It's still 98%. So now you see here that, let me see what it's learned. It's actually, it does look like it's come closer to learning. If I compare, or is it the same? It looks like, from what I remember, it's closer to learning the boundary. And if I increase this, let's say to 1,000, let's see. What if I increase this to 10,000? There you go, 99%. So it's trending to and a very cool looking thing on top of that. If I zoom in on, it's having a hard time because there's so many data points. Can I zoom in here? So let's actually not draw. Let's see if this will work. No, I want this, but I don't want this. Actually. So here, what I'm showing is, you see, it's come very close to learning the true data structure. The data structure is the unit circle, and the So one of these is the true boundary between the two classes, and the other one is what has been learned. And you see that what has been learned is very close to the truth. And then if I go back down to 100 and I repeat this, you'll see that it will be different. You see that it's not even circular anymore. And so simulations are good because they let you never, like in a real application, you never have the ground truth. Like you don't actually know what the true distribution is. It's not observable. But simulations like this are great for, for teaching, but also just for testing, doing sanity checks on your model. So one thing I always do when I write any kind of learning algorithm or add a learning algorithm feature, one of the first things I'll do is I'll run it on like a Gaussian example. So where one data is a Gaussian with a mean, and the other data is a Gaussian with a different mean. And then I look to see whether it separates that. And so that's good. It's helpful to know what the ground truth is. It's helpful to know what the theoretically optimal solution should be, because then you can see whether your algorithm is actually doing that. Okay, so if there's questions, feel free to jump in. Otherwise, I am going to conclude our discussion of support vector machines and move on to deep learning.
Which kinds of data actually have this distribution that like it would be useful if it's separated radially?
Yeah, it's a good question. Let's see. So it's not, as I was saying in BME, the data usually is separated by angle, by the direction. So it's not so in the cancer example, I was thinking about the cancer example. And so the radial basis function, example, kernel, is good when, I think it's good for images. It's a short answer. And the long answer, in going back to the example of the brain scan, let's say that a malignant tumor can appear anywhere, but it's always bright. And a benign tumor, benign tumors are just always darker, let's say. So if in general, I think the answer is, if in general, like if you have, let's see, let's say you only have 2 pixels, 2 voxels, and this is voxel 1, and this is voxel 2. So the radial basis function is good when the malignant tumor is just brighter. It's not brighter at any particular voxel, it's just brighter in general. And so you're just like, you're occupying the part of the space that's further away from the origin, period. But the direction doesn't matter, which means that, if I have, let's see, if this is voxel 1 and this is voxel 2, it's not like in a malignant tumor, this voxel is always brighter than this one. Sometimes this one is brighter than this one. Sometimes this one is brighter than this one. So there's no relationship between which one is brighter, but in general, they are usually brighter than a malignant tumor, than a benign tumor. right? And so a benign tumor is just going to be lighter in general. And so I should probably take the time to make a slide out of this, but the idea is that I think images are good examples because, you know, any kind of a scene that is just generally at at higher contrast or higher intensities may just be further away from the origin in n-dimensional space. So I think the short answer is images. Okay. And the ways in practice, you just always test different kernels and see which ones work well on your data. All right, so this is one of the first section of the course on deep learning, and mostly the goal here is just to orient you, give you the background, and show you on a very simple toy example why neural networks are necessary and why essentially linear classifiers are inherently limited in terms of their ability to separate classes. Okay, so this is a field that has seen a lot of development over the last 15 years. It's been very application driven. So support vector machines were developed mathematically. So the equations basically that went into that constraint optimization problem were worked out, and then the support vector machine model was available and was then applied to different types of data sets. Deep learning has been driven by advances on practical problems in AI, natural language processing, which is like translating text from one language to another, speech recognition, which could be waveform, taking in a waveform and transcribing it into text, could also be just recognizing who's talking, that's speaker recognition. And then there's the big one, which is object and face recognition, which basically learns to identify individuals or objects from natural images. And so the first thing to note is that the deep learning refers to the architecture having many layers and nothing to do with the depth of knowledge learned by the models. And nowadays it's very common that to have deep learning be used interchangeably with machine learning, but the two are not actually the same. Deep learning is a subset of machine learning, and it's the most popular kind of approach to doing machine learning right now. So before we get into how to actually run these models, how to train these models, just a disclaimer that it may not work best on your specific problem. Number one reason for that is deep learning models generally require a lot of training data. So a model like this is a shallow network and this is a deep network. So this model has many more parameters than this one. And as a result, to figure out the weights of all these connections, the model needs to be, the outfitting algorithm needs to be exposed to a lot of training data so that it minimizes the prediction error between the true label and the prediction. And so the red nodes here are the inputs. So the inputs here could be the intensities of your pixels or your voxels. It could be things like weight, height, age, heart rate, heart rate variability. The nodes to the very right, those are your output nodes. And that can be something like, let's say this picture here corresponds to a 4-class problem. So for example, could be no tumor, benign tumor, early malignancy, late stage, like severe malignancy or something. So if you have 4 possible outcomes, that's what this is modeling. And the nodes in between, these are called the hidden nodes. And this is where the learning really happens. And so one way to think about this is that each layer is learning a progressively more intelligent facet of your data. And so I've used this example before in images, but maybe I'll use it now in terms of brain scans. So these will be your MRI voxel intensities. These first 2 layers may represent things like, shape, maybe your contours, and then the later ones will actually represent things like, irregularity, or I don't know, a certain texture that is very good at identifying the type of tumor that this is. And so as you go from input to output, the model is trying to learn more and more abstract representations of the data. And so the artificial neural network, so there's neural networks that are biological, those are in our brains and the brains of all living things. And there's artificial neural networks, which are just a class of algorithms. They've been around for a long time, but only recently have they really taken off because of deep learning. So then, despite what the name says, they're only loosely inspired by actual computation in the brain. And so the big difference between the way that a biological neural network is structured and the way that an artificial neural network is structured is that there's generally much more feedback in the biological brain than there is in the artificial brain. And so a lot of what the brain does is rooted in predicting what's going to happen next. And it's like a common theme that whenever you encounter a stimulus that is surprising, you often see a very large neural response to that. And so I think at a very low level, I think on multiple levels, multiple scales, what the brain does can be thought of as predicting what's going to happen next. And so you've probably noticed yourself doing this. Like I definitely have. As I've gotten older, I noticed that I consciously become aware of the fact that if I'm in a situation, let's say I'm in a social situation, my brain is actually actively making a prediction of what it thinks will happen next. And sometimes I'll actually hear that prediction verbalized, like internally, of course, in my brain. And I don't know if you guys have had that experience, but I definitely have. And if you're interested in this topic, there's a wonderful book authored by Jeff Hawkins called On Intelligence. So Jeff Hawkins is actually a very interesting guy. He is the founder of the Palm Pilot. You guys probably don't know what that is, but the Palm Pilot is basically the first ever smartphone. And it actually became quite successful. And so Jeff Hawkins built a Palm Pilot, but he was always been interested in how the brain computes. And so I think he kind of is leveraged his commercial success, his business success, to create kind of first it was a neuroscience institute, and now he's running a company that basically does research, neural research. But his book On Intelligence, which I highly recommend, it's not a difficult read, but it's also very insightful. It's all about this premise that what brains do are essentially predicting. Brains are prediction engines. And the reason I bring this up is because feedback is what implements, I think, that prediction in the brain. So for example, the neuron is getting, let's say that this is a neuron in the brain, and this is, these are its inputs and these are its kind of outputs. So this is downstream. So the downstream neuron will send a feedback signal to this neuron to kind of convey what it's gonna see next. So even though the red node hasn't yet sent the information over to the yellow node is already kind of knows what's coming next. So that's happening with feedback to the yellow node from this green node. I don't know if it's green or blue, but so that feedback element is generally missing in deep learning. Like there are architectures that have feedback, but in any 99% of the networks, the neural nets that you see online, they're purely feed forward. So the information goes from input to output, directionally, and there's no passing information back down in the direction of the input. So that's one way that artificial neural nets are different than biological neural nets. So the brain has a lot of I think the brain actually has more feedback connections than feed forward. The other big one, of course, is that the biological neural networks are general purpose networks, right? There's a lot of overlap in the circuitry. So in AI, if you want to build a language translation tool, it's not straightforward to then take what has been learned and use it to categorize cats and dogs. There is work in that field, and truthfully, there's probably more progress there is progress in that area. It's called transfer learning, and there's probably a lot that I'm not even aware of in this space. But in generally speaking, artificial neural nets are not good at, it's not general intelligence. They've been trained to solve a very specific problem. And the way that, the reason that neural nets were, I think the initial motivation behind the neural net is that mathematically, there's a function that this is X here. I should probably indicate this. This is X, and this is Y, and Y is a function of X. And then this will be H. And so the idea is that H is here. So the idea is that, and actually to be more truthful, it was something like Y is a function of H, which is itself a function of X. So you get this kind of, what is this composite composite function. So what neural nets are doing is essentially they're performing many composite functions. And so if you had an extra layer, if you had an additional hidden layer, you'd have something like GH2 is equal to G, let's say FH1 is equal to G of F of another letter. Let's see. Let's use E of X. So what neural nets are doing is every layer is kind of adding an extra transformation of the data. So in the example that you see here, you just have the transformation from input to hidden layer, and then from hidden layer to output. So that's this here. And so it's gonna, right, so Y is a function of, actually, you know what? Do this properly. This is H, and so Y is a function of H, and H is a function of X. And as a result, Y is a function of X. And so Y is a composite function of the input X. And what's really, one of the key elements here that I'll describe later in a few slides is that there has to be nonlinearity in each of these nodes. So every H is it's basically like a logistic regression, a logistic function. Each of these H's is performing a different version of a logistic with different weights. And so there's something called the universal approximation theorem, which states that you can represent any function between X and Y with a single hidden layer. So even though this only has one hidden layer, this architecture here can literally synthesize any mapping from X to Y, which is very powerful because it states that you never need more than this. In theory, if you have an infinite amount of data, this architecture will be able to learn this. It will solve your problem. It will map X's to Y's. And if you give it enough data, it will actually capture the true mapping. However, what has been discovered empirically is that just because you can represent any mathematical function, does it mean with a single layer, doesn't mean that you can learn it efficiently from a training set. And so what has been discovered is that this is generally, it is not a good idea to put all your learning into a single layer. And the explanation for that is, it was mathematical. It's way beyond the scope of this course, but essentially, intuitive, I guess the kind of intuitive way is that if you look at the number of parameters required, you get a boost in the flexibility of your network when you stack layers. And there's actually a picture coming in later on that will kind of show this geometrically. The idea is that you're better off having two simple functions that are cascaded than you are having one larger function. And there is some theory behind that. So, and that's the idea of how you represent a function. So that's what supervised learning really is. It's learning, it's trying to figure out, it's trying to infer the nature of F from X and Y. Okay. Right, so even though the universal approximation theorem states that all you need is this, but unfortunately, if you put all your parameters into a single layer, you'll generally not do a good job in the model fitting process. You're going to overfit, basically. All right. So, right. So this slide is basically kind of explicitly stating what I said on the previous one. So I've just taken the neural net picture from before and I've just rotated it by 90 degrees. So the inputs go here. So your input vector, one element for each of these red circles. And then this H is called the hidden layer or a hidden vector. And so what is H? Well, H is just a linearly transformed version of your data, and then pass through a nonlinearity sigma. So sigma it's called a static nonlinearity. It's also called the activating function. And so let's see how much time do I have here. So each element of H, each of these yellow nodes is like I said, it's one logistic. So if you think of sigma as just being the sigmoid function, each element of this H vector is just the output of one sigmoid. And each sigmoid has a different weight though, right? So each of these 7 sigmoids has different connections from the input to its output. And so let me see if I can ask this question. So if I have, the question I want to ask is, why do I need this nonlinearity? What's wrong with just stacking? So if I have H is equal to W transpose times X, and then I have Y is equal to, let's say, V transpose times H, right? What's wrong? And then, so in other words, Y is equal to, if I just do substitution, right? So I can write, so if my hidden layer is linearly transforming X, and my output is linearly transforming my hidden layer, I can just do this. So why is this not a good idea? Why do you guys think that this activating function is needed? What's wrong with just having a bunch of linear transformations?
You don't really gain anything because you could just combine them, right?
Exactly. You don't gain anything. It is equivalent, right? So the idea is that because of the linearity, right? Y is just, and this is just a matrix M, right? Where M is equal to V prime times Y, V transpose times W transpose. So you're not actually, so at the end of the day, you're not actually doing anything different to your data than you would if you had a single transformation, right? So that the added layers don't give you anything because of linearity. I'm trying to think of what the property is. So yeah, I guess it's linearity. So no matter how many matrices you multiply together, at the end of the day, they can be combined into a single matrix. And so that's one way of understanding why the nonlinearity is there. Another way, and I think a way that is useful for those of you that don't like to think in terms of algebra, and that is that certain variables just inherently have a nonlinear relationship between them and between. So for example, what's the example that I like? I think I gave this example last time, that the relationship between exercise and heart health, right? If I'm trying to predict heart health from exercise, I know that the more exercise, more exercise does not always translate to more heart health. But But if you just ignore the fact that you can actually have it can be, so monotonicity is not a bad thing generally. H of x, or let's not call this H, let's call it sigma of x. So sigma of x is usually some kind of step function like thing. So the activating functions and some so that's a sigmoid. You also have the tan H, which is very similar. You also have this kind of hinge function. So there's these activating functions are usually simple, but they're always they're very rare. No, they're never like non-monotonic. I don't think I've ever seen a non-monotonic activation function sigma. And so so another way of thinking about why these nonlinearities are necessary is that there are just certain variables just saturate. And so, you know, in the brain scan example, for example, you know, whether a voxel is very bright or extremely bright doesn't necessarily increase. Like there may just be a certain voxel intensity where if you hit that intensity in the image, you're basically, let's say for simplicity, you're guaranteed that this is a malignancy. And so if you increase that intensity more, I don't want my model to increment the probability. I don't want my model to increment the weight of that voxel even more, because there isn't actually a relationship in the data. So that is another. So this is a super important slide that I'm gonna go back to when we meet in person on Monday. That is it for today. So I will see everyone back in person on Monday. The homework is due, I think, tonight at midnight, although I've told people that if they need extra time, I'm always happy to grant an extension. Just let me know. And the 24-hour data challenge will take place on April 11th. Just think of it as a really condensed homework. It's going to be a Matlab exercise with instructions, with data that you will then have to analyze over the span of 24 hours. Bye-bye.
Thanks.